Welcome to Headwater Science Center Earth Week special. Well, what are we doing this week? We're caring for the Earth, and how do we care for the Earth? We care for the Earth by caring for the equipment that we use to measure the Earth. We're scientists. We think in terms of numbers. We do our statistical analysis with numbers. So we need numbers in order to talk about what it is we're trying to say about a particular something or another. And there are many somethings or another. So let's talk about three somethings or another that we do deal with in the field. We do some of our chemistry in our lab. Water chemistry, surface water is what we focus on. But out in the field, we conduct numbers and research and data analysis on conductivity. Now, conductivity is a good indicator of things that are dissolved in the water, and this time of year there are many things dissolved in the water. The chloride, potassium chloride is one of them. There's a mixture of chloride that they use on the road salts. There's the pollution. There's the nutrients that have been sitting up in ice that are moving into the aquatic systems now. So we're looking at things that are dissolved in a conductivity. While it doesn't tell us what we're looking at, it tells us what kinds of things we're looking at. We're looking at metals, things that make the water more conductive. Water is neutral, so when it conducts better than you'd expect it to in its purest, cleanest form, you go, why? And so then you can look further for other things. And some of the things we do here are just a way to how to look deeper in our laboratory. A couple of the other things we measure in the field, it's because they're accessible by equipment that's easily calibratable, and that's what we're that's what we're going to be doing. Dissolved oxygen. This is necessary for life. If you don't have levels of about 5 or so, fish don't do well. But if you don't have levels of 2 or more, then some of the bugs and things in the water don't do well. So you need oxygen in the water. Well, some people wonder, where does it come from? Well, it comes from the air. It dissolves into the water. Now, up here in the atmosphere where we live, there's always a healthy 160 to 200,000 parts per million. Down in the water, we're talking 5 parts per million. We're talking 3 parts per million in some places, and that's a typical range. And so it's a lot more scarce. It's the same oxygen, the gaseous oxygen that the fish use, but they're much more efficient at getting it through their bodies. And so we want to get that at some acceptable level and know about that. The other thing we look at in the field, because it's easily detectable with instruments and it changes, is pH. Now, pH is probably the most... I should say pH is the hardest to say exactly what it is and why, but the differences between different pHs, and pH represents how much potential hydrogen ions, are in the water, or hydroxyl ions. So if there are a lot of hydrogen ions within the pH goes down, it goes low, it goes towards acid. If there are a lot of hydroxyl ions, pH goes up, it goes towards the basic side. So we generally want water to be somewhere between 6.5 to 8.5. That's that range where life tends to want to exist. And we ourselves live in that range. Our body, if you put us into a grinder and slushed us all together, we'd be about 6.4 pH. So we're slightly acidic. Neutral is 7. We care about pH for other reasons than whether it's in that range, because different chemistry acts differently. It reacts differently under different pHs. Some things precipitate out of the water at higher pHs. Some things dissolve into the water at lower pHs. So we want to keep that pH in a reasonable range. All right, well, let's look at that, because we do have to indeed calibrate our instruments every time we go out for a day's worth of sampling. We like to have our instruments calibrated, and we're calibrating so that we can come up with 2 kinds of assurances. And the 2 assurances we're most interested in are accuracy and precision. They're slightly different. Sometimes they get thrown together. This cap on there keeps that pH probe.
What's the difference between precision and accuracy?
Between precision and accuracy. I'm going to go into that. So precision relays if what you're measuring is exactly what's occurring. In other words, when I see a reading of, say, for instance, 7.2, is that really what it is? So we want to get the precision to be to correlate perfectly, if we can, to what the actuality is. Accuracy relates to how many times we can do that in a reasonable manner that we can trust that that measure is true and so. So when we first go out, our accuracy is good, and hopefully our precision is as well. And as we go through the day, those two can, either of them, both of them can fade. So let's look at how we can find out two things at once when we start to do our analysis. We can find out how well we did the last time out, and we can get ourselves ready to do it well again the next time. Now, I do a 3-point check on pH. It's really only necessary to do a 2-point check, but I feel so happy when I get my third calibrate in and it measures out well and shows me that yes, your meter does show both accuracy and precision. So what I've sprayed on there is deionized water. This is pure H2O. It has a neutral pH. It has nothing really on it except it's pure molecules of hydrogen and oxygen. So I always start in the, I'm going to turn it this way so you guys can see that, with the 4.0, and that's the low end of the pH. That's very acidic, and I put that in there. And what the first thing I do, and this helps me decide whether the last time I was out I had some good readings. I read it. I get the measurement of a solution that's 4. Is it 01? Yeah, 01. And my meter says in the 4.01, it's measuring to, hasn't stabilized yet. These meters are pretty fast, and so it's measuring out to 4.05, which tells me, you know, that's the first measurement from the last time out, that I was pretty close the whole time I was out last time. So what I get in, once I'm in the water, now I do a shortcut here, and that is I've already cleaned my probe, and then I do a calibration read. So I'm going into it and I'm going to calibrate it from there because I want to get it down to 4.01 or wherever my meter has decided the proper pH would be. pH is related to temperature. It's how much related to electrical activity. One thing that can change it is these meters have electrical things that can change. So I'll calibrate it at that, get the calibration going, and the meter that used to read at 4.05 now reads at 4.00, closer to where it was. So it was off just by a touch, and this meter told me, yes, you passed the calibration for 4.0, and I'll store that in there, and I'll have that first calibration set and met. And now it has a 4.0 on its probe, so I have to rinse that away. And you have to do this every time because now the meter is carrying 4.0's worth of reaction. So let's get that well cleaned, and I like to get right in there. This is a glass probe, and so it's a little sensitive to breakage. I want to climb up in order, so I do a 7 calibration as well. I'll put that one in front so you can see that, and I'll shake it up. Now that doesn't have very much buffer in it, so it's going to take this new pH and bring it right to where it is. These 7.0s are tight in the canister. These are field pH standards, so they're built to make it easy, and hopefully that helps you out here. Again, we're going to read it, and sort of it should come in around 7. 7.13, but it's still, the meter's still kind of trajectorying itself towards calibration. We'll calibrate it for that, get it going. So it was okay down in the acidic range, and now the mid-range, we've got it calibrated to 7.02, which is the right calibration for this temperature, which is, by the way, 65.2 degrees is where we're calibrating this stuff at. Fahrenheit. All right, so I'm going to clear it again, get it rinsed well, make sure it's even good. Sometimes I even put that under the sink first, the tap water, and then I do this to rinse the tap water off, because the water itself can interfere with our calibration. Let's move it to the final one, which is the 10, and usually by the time I get to the final calibration, it can find itself close to where the standard is. Let's put it back in there. Shake it off. Let's get it down in there. So there's a little bit of solution down at the bottom of each one of these packets. And again, they're made easy for the field. So let's store the last one. And we're predicting a 10. I'm already to 9.97, settling in at 9.99, 10. We're going right in. The first one is the most telling on whether the last sampling was good or not. If that first standard reading is way off, you go look at your data that you just pulled in from the last session out and go, and you would probably put a notes into your field to suggest that maybe you've got some questionable ideas. It's not telling of all, but it is alerting to something. So we came back at 10.05. We'll calibrate that. I think it'll actually calibrate a little higher than that. We'll see, because we're here at this cooler temperature, and it is calibrating a little higher at 10.08. So that's what this temperature and this amount of electricity has decided should be the proper pH of that solution. So now one more thing we got to do before we put the pH into that. Now the meter stores all this stuff, so I can, if I need to show my the record of my pH, I can do that later. So the one thing we always have to do is make sure that this is packed back up. In here I use a pH storage solution. It's a potassium chloride absorption. It keeps the end of this glass probe moist. Now the moisture or the water content of this probe equals 100%, which is the same as the water, and so it always has to stay wet, and that keeps that meter working well. pH is the one meter that actually does drift the most of all of these readings we do out here. pH probes tend to be the most unreliable, and but we work with it because that's what the equipment limitations are. Now the other thing we're gonna calibrate right now is the conductivity. Now that's this probe right here. Put that in there. Maybe I'll loosen that up a little bit, get the meter disconnected from pH. The meter's going, where's my probe? I'm gonna put you right on there. Now if you're doing this, I'm gonna move this for you, and you're doing this with our equipment, I want you to do it right. So I'm gonna try and tell you how to do it right, and how to do it right is the way I do it. And the way I do it is the way it's done by the Pollution Control Agency, by the way they take data in the state. And so I feel like that's the kind of thing you want to do. When I calibrate or when I sample, I go out there as though I'm going to end up in court. Now, I actually have been in court before. My data has. They gave me a call the day before and said, oh, your data's going to court. And then they took my name and some numbers. So my data went to court, but could you be available to come in and support it should it need it? I never had to go. The long and short of it is I've had data in court, but I didn't have to go to support it. But they called up and they said, your data looks good. We don't need to question it, but you want to make sure that you couldn't have a zealous lawyer shoot down your data. Presume you're going to court with it. All right, so I cleaned that up, rinsed that through, and here we're measuring conductivity. Now that standard came out of this bottle. That's 1,000 microsiemens per centimeter. That's just the unit. Another way that it's talked about is in a term called mhos, but that's just something you might run into. But microsiemens per centimeter, and that's relating right on the meter. And again, we're going to check the last time out to see how we did. First thing I do is I read the standard, and the standard should come back at 1,000. The standard's coming back at 1,000. 999. So that tells me that my last readings out there in the field were probably pretty good, because I'm coming back in the standard and I'm getting a good number. 999 is right next to 1,000. That's 0.01% where the actual truth. We'll get that calibrated, and the meter does some hocus pocus, some mathematical curve smoothing, and we're done. We'll store it, and I like to be patted on the back to make sure I did all my calibrations right. So I always do one more reading, and my reading comes back at 1,000. Oscillating between 99 and 1,000. What's telling me is that the meter wants to drift the other direction, but that's fine with me. I can live with all of that. So let's take this one away. Let's put the guard back on, clean it up. That's really just a sodium chloride solution, but it's been preserved into its good form. Put that back on, and then we'll do our final calibration for dissolved oxygen. Now this one's my favorite, for silly reasons, of course, but partly because it's a little bit mysterious. these others to put them in the solution. The solution was made by a company that overcharged me for these standardized ideas, but this one I like because you have to use physics in your reasoning here. So I'm going to hook up that dissolved oxygen probe. Again, as you probably figured, I got to go through the same process. Again, we're measuring in milligrams per liter, which is the same figure as parts per million. If you think about milligrams, that's 1,000, liters 1,000, 1,000 times 1,000 is 1,000,000, and that's kind of where we get to our parts per million. Remembering, of course, that the oxygen down under the water is quite low, so we have to make sure that we have a good range. I got to get a chem wiper right here. That's the one thing this thing is a little particular about. These are chem wipes. They'll be in your kit. Oops. They'll be in your kit, and they're really, we use them at this calibration point. You want to always inspect the meters, but especially this one, because this one has a somewhat fragile probe end here, and we want to make sure there's no marks or dings on there, and it looks good, and we'll see if we can do that. Now, what we're going to do is we're going to actually calibrate that in pure water. That's our reagent here. That's water that we've filtered out through our system here. It's deionized. There's pure H2O. And what I'm doing is I'm shaking it. As you see, this model's almost filled up completely with that liquid. And I'm shaking that because what I want to do is create a 100% humidity right there. That means it's totally saturated air. And so when I shake it like this, right now it is totally saturated in that area where I'm going to measure, but I'm going to shake it up, shake it up, shake it up. And I always feel like I got to be quick on the go with this one. So I'm going to get that out there quick and then get that meter in there. Now, again, I don't read this one first, though. This is the only one I don't. I'm going to go right to calibration, and this actually takes a little while. And now we have a little time to talk about your question in your mind, and you should have that turned head look and go, yeah, but if I look closely, I see you're not in the liquid. Well, the water isn't 100%, which is where I'm calibrating to. Saturated with dissolved oxygen, but the air is, because it's the air that has to saturate. So from a logical sense point, we're going to have, we get that going. So we had more time now to explain why I like this one the best. So right now it's trying to find that 100% saturation in air, which is a lot harder actually to do, to find the actual saturation in the air than it is in a liquid, because this meter is actually designed to find oxygen in liquid. But if we can find 100% in the air, like we should, we can use that air itself as the calibration from that pure H2O saturated air. And this is moving in and clanging forth. And the way that the new DO meters work, it used to be with more of a pressure situation. They used to use a light and a couple of light shots through it to give it. It almost, I don't know enough about the meter to give it to you, but it almost looks like it's looking at red and blue shifting. And so it's sort of, a red light and a blue light will come by, and that tells me, oh, everything is good, everything is great. We're still, the air on top of that is 65.5, similar to what our others. So apparently the temperature in our air here is 65.5. So we're working forth with that. We're almost there. I've got about 2/3 of my calibration made. Now, when you do this, if you just took the meter out to take one measurement, okay, whatever. But if you're going for a day sampling, I want a good meter out there, because you don't want to waste a day's worth of driving about and getting data. I can remember some times and some stories in the field where we had people gathering data and falling down, and everybody's going to catch the samples and let but they weren't seriously stumbling. I'm just wanting to tell you, the data is precious. The samples are precious. You can't go back and relive a moment, so you have to take a different data point in the universe if you lose a sample, which is why I always take 2 samples, or enough sample to do more than one measure in the laboratory. It being stubborn on the calibration there, but it's going to give us a good reading when it does. Meanwhile, let's double down on what else we can do. I've just cleaned out the sampler. It's over there. Maybe you can point over to that. I have to use a super soapy solution that's assembly line, food assembly line quality, to make sure that the samplers themselves don't leave their mark on the data, on the water samples. So we will gather in those, and another sample, and perhaps the one we do this Friday, we'll show you how those work out in the field.
Let's show. I'll hold it up. You say what it is.
Okay, so it's all in pieces. I take it all apart, and and this is the horizontal sampler. We'll drop that down to the level we want to take our water sample at, and the two ends of it will be connected by a rubber band, and they'll close and hold the level. So when we sample in rivers, we sample 1/3 down, 2/3 up. When we sample in lakes, we go to the deepest part of the lake. We take a surface reading. We take a reading every. Then we get a deep one that's just off the bottom, and then we take one every 10 feet in between. We really want to find it out. Now this thing is really being stubborn about finding its calibration, so I got more to say. We have to make sure that the sampler itself, again, doesn't bring. I clean up the box. Right now I'm soaking the rope. I make sure I don't introduce anything into the sample that isn't there naturally, and this is really not going towards the stabilized condition. Now this will, I know it does sometimes take a while. I'm going to hold that like that. Sometimes if I just look away, it decides it wants to do what it wants to do. Let me see what else I'm going to talk to you about here today. There's that. We have two kinds of samplers here that we use. Essentially, we use that horizontal sampler, and then we use this pretty low-tech device, which is a stick and a bottle. And so this stick extends. Don't let me down, sampler. This stick extends, it connects up to the bottle, and so if I want to get out into the water, I don't have to get my feet wet. Because one of the reasons we actually don't want to get into the water is because when we get in the water, we introduce ourselves to the water, so we can sometimes not get the true good sample that we wanted. Well, let's just say this thing did what it was going to do. It's getting there, starting to move. It usually takes less time than this. Of course, we're on camera, so it's going to be stubborn about it. There's always a stickler in every show. Usually it's me, but today it's the DO meter. Reminding everyone that this is Earth Week. I'm not sure. Earth Day is coming up. I actually was thinking earlier, wait a minute, Earth Day? Huh? Shouldn't it be Earth ever, forever? Yeah, well, I guess we had to have a day. But this time of year, generally speaking, the Science Center will go out and do some kind of Earth intense program somewhere and have more of a celebration of how fabulous the Earth is. But we really do some work behind the scenes. We make sure we've been working Riverwatch data for years. We've been keeping track of some of our waters around here. Lake Bemidji is probably the most studied lake in the world. There's a university over there that's putting out degrees in fisheries research, in aquatic biology and things. So it's a well-studied lake, but we like to be part of that well-studied portion of the lake. And we're famous for going over there and capturing not only data, but a critter or two that we sometimes let our kids showcase in our museum from time to time so that we can study them. And we always like to treat the animals that we capture, whether they be a bug, somebody's food that day, or maybe a creature like an invertebrate like a fish. We treat them with integrity and decency because they'll give their lives for this work and to be study and interesting elements for our entertainment. So the meter actually is moving, but very sludgily, so it truly probably needed a calibration here. This is one of my newer probes, so it shouldn't be this bad, but usually I wouldn't have to say this much while I'm waiting for a DO meter, but if it won't go, we have to sometimes start it up again and try it again. But it looks like it's starting to close in, and while it does that, I think we can't just hold your attention out here. We're going to call that the how-to on calibration, and you can refer to this video or some sense of that. I would like to thank Beltrami Electric for their Rounded Up program. They helped fund this tutorial on calibrating meters. Oh, now you're gonna go, okay, well, I guess we're gonna have to go because me looking at a meter just isn't gonna hold your attention too much longer. So thank you for tuning us in all the way from, where was our farthest?
Well, we had somebody from Brownsville?
Browerville we took. That's middle of Minnesota, I think mid-Minnesota, somewhere in Browerville.
We've had a lot of folks in our Twitch chatting along and watching.
Oh, just chatting along.
We have one person from the Netherlands. So
Oh,
yes.
so we're catching far and wide. Maybe they're using
Although
the
I
same
think
equipment.
you win.
This Hawk equipment is pretty much the standard for, affordable but effective water sampling equipment. It's been the standard for 10 years now. Of course, so it helps that we're all using the same stuff. It's how it's been done. I'm moving in on my calibration here. Oh, I think we're gonna get the pretty colors. Wait, stay, don't wait, we're gonna get the pretty colors. Here they come. Oh.
Haro, it's meme, is the person from the Netherlands, and they say thank you.
Okay, well, I wish we could have more fluent and flowing conversations between each other, but pretty colors are coming right now. You'll see them there. That's when you know your calibration's occurred. Pretty colors happen, a little red, a little blue, and the meter said yes. Let me see how close I was. 106.5. So I was a little off. This DO meter was slipping about 6% off. Now it's recalibrated to 100%. And when we go back out there, we'll be both accurate and precise.
You have been dubbed Science Santa, by the way.
Oh!
You are the helper elf.
I took off my Santa length the other day. So this is the first one we've done here without a mask, so we are in our vaccine bubble here. So don't worry for us. We're okay.